Calculus 1 is about a process called differentiation. Before you learn about differentiation, you must know everything about functions. But what is a function? A function can be represented in different ways. It can be written as an equation, such as y equals x squared, or as a set of ordered pairs. And since it can be written as a set of ordered pairs, we may also use the set builder notation, such as y equals x plus 1, such that x is greater than 0. A function may also be represented using a graph. But how do we know that these are functions without knowing the true definition? There are many ways to define a function, but all of them mean the same thing. A function can be defined as a set of ordered pairs in which no two distinct ordered pairs have the same first numbers. The last part, no two distinct ordered pairs have the same first numbers, differs it from the term relation. A relation is simply a set of ordered pairs. So any set of ordered pairs may be considered a relation, but not a function. Here is an example of a relation that is not a function. As you can see, it satisfies the definition of a relation, which is a set of ordered pairs. But it does not satisfy the definition of a function because of the first two ordered pairs. Going back to the definition of a function, no two distinct ordered pairs must have the same first numbers. And looking at the first two ordered pairs in our example, they have the same first numbers, which is both equal to 1. So it means that this set of ordered pairs is not a function, but simply a relation. What about the next example? Is this a function or simply a relation? Look at the ordered pairs. Do you see any two distinct ordered pairs that have the same first numbers? We have 2, 0, 5, 0, 1, 0, negative 5, 0, 10, 0. Although all of the ordered pairs have the same second numbers, which are all zeros, we did not say anything about the second numbers in the definition of a function, so still we consider this set of ordered pairs a function. So the first example is not a function because of the first two ordered pairs, and the second example is a function. What about the third example? If you try to look at the first two ordered pairs, the first number in the first ordered pair is the second number in the second ordered pair. Do we consider this a function or simply a relation? Again, we go back to the very definition of a function. Do we see any two ordered pairs that have the same first numbers? Look at the first numbers. We have 1, 5, 2, 4. No two of them have the same first numbers, so we consider this a function. Now you already know how to identify a function if it is written as a set of ordered pairs. What about if it is drawn as a graph? How do we know whether a graph is a function or not? Say we have this parabola opening upward with vertex at the origin. How do we know if this is a function or not? It's actually very easy to identify using a vertical line. We call that vertical line test. We can draw a vertical line passing through the graph. just like that. If the graph and the vertical line that you have drawn intersected in exactly one point, at exactly one point, then we may consider this graph a function. This is a function. On the other hand, if you use the vertical line test, and then you've noticed that the graph and the vertical line intersected more than once, such as this, first intersection, second intersection, then we say that this graph is not a function. So a circle is not a function, because using the vertical line test, we can see that the circle and the vertical line intersected here and here. So they met twice, first here and then second at this point. So therefore, a circle is not a function. Again, we use a vertical line test to identify whether a graph is a function or not. But if a function is written as an equation, how do we know whether that equation is a function or not? One example that I gave a while ago is y equals x squared. How would you know right away that this equation is a function? The easiest clue would be look at the exponent of y. If the exponent of y is 1, such as this, well, we know that this has an exponent 1. So if the exponent of y is 1, such as this, then the equation must be a function. If I change the exponent of y to 2, then we'll have the equation y squared equals x squared. This will not be a function anymore. The equation y squared equals x is also not a function. How do we know that? Well, this equation means for every two values of x, there is exactly one value of y. Now, on the other hand, this equation means for every value of x, there are two values of y. Now, this violates the definition of a function. You see, if I were to write this as a set of ordered pairs, then I would have, when x is equal to 1, what's the value of y? Y equals 1. Or, y can be negative 1. Then I would have the ordered pairs 1, 1, and 1, negative 1. See, when x is equal to 1, y can be 1, or it can be negative 1. So for every x, such as this number, there will always be two values for y, 1, negative 1. Now, when x is equal to 4, y can be equal to 2 or negative 2. Why? Because 2 squared is 4 and negative 2 squared is also 4. So again, this pertains to the ordered pairs 4, 2 and 4, negative 2. Again, violating the very definition of a function because you now have two ordered pairs that have the same first number. First numbers, 4. Now, what about for the first equation? Y equals x squared. See, when x is equal to 1, you see y is always equal to 1. When x is equal to negative 1, y is also equal to 1. When x is 2, y is equal to 4. When x is negative 2, y is equal to 4, giving us the ordered pairs 1, 1, negative 1, 1, 2, 4, negative 2, 4, and we can go on and on. But you will never see any two distinct ordered pairs that will have the same first numbers, because if I repeat 1 for another ordered pair, say I have another ordered pair with the first number 1, then in this equation, when x is equal to 1, then y will also be equal to positive 1. And I'm going back to the same ordered pair. Now the question is, what if we change in this equation? What if we change the exponent of y to 3? Y cubed equals x. Or maybe y to the 4th equals x. Or maybe, better yet, y to the 5th equals x. Are these functions or not? Or are some of them functions? This is a question that you need to know for yourself. Now, going back to the function y equals x squared, may I introduce another notation for a function? Okay. Y equals f of x. Some mathematician, I don't know, Euler, introduced this notation, which means, well, this means the value of the function. Hence f. We read this as f of x. So instead of writing y equals x squared, we may write y equals x squared as f of x equals x squared. Now, if I want to use another letter, say t, I may also write this as f of t equals t squared. If I want to use letter r, I may write this as f of r equals r squared. I may also use capital F, like capital F of x equals x squared. Capital F of t equals t squared. Capital F of r equals r squared. I may also use g, small g or capital G, g of x equals x squared. G of t equals t squared, and so on and so forth. So what are the usual letters that we use to denote functions? Well, F, and its capital letter, G, capital G, small h, capital H. Well, you may use any letter that you like, but these are understood as functions, at least when we're talking about calculus. Now you know how to identify a function, whether it is written as an equation, as a set of ordered pairs, or drawn as a graph. Now, let's move on to the next. Generally, or at least in pure mathematics, a function is written in this way. F, colon, we use capital letter A, and then a line with an arrowhead, and then goes to B. Now, what does this symbol mean? Well, this means mapping. First of all, this means function, hence F. Okay. function, and then the first letter after the colon, this is the domain of the function, while the second letter, this, means the codomain of the function. So it means to say that the function f is a mapping from the domain to the codomain. So what does mapping mean? I will just draw it for you. But first you have to know that both domain and codomains are sets. Or these are set of numbers because we are in calculus. Real numbers to be more specific. Now we have two sets here, the domain and then the codomain. Let's have it in green. Okay? So if a function is a mapping from the domain to the codomain, in the figure it must be like this. Like that. This is our function f. But what's in the domain? And what's in the codomain? Well, I have to be specific, more specific in my function. Let's say I have a function f from the set of real numbers to the set of real numbers. So this is my domain, this is my codomain. Both of them are representing the set of real numbers. So what's inside this are real numbers. And inside this codomain, real numbers also. Now, just for the sake of the discussion, let me take the function again, f of x equals x squared. Okay, we'll be working with this. Now looking at that function, if in my domain I have 1, okay, then in my codomain I have 1 also. Why? Because when x is 1, f of x, or that is the value of y, right? Using the older notation that we have, is also equal to 1. Now when x is negative 1, f of x, or we may write f of negative 1 is equal to 1 also. Now we have to change this to positive 1. Okay? So when x is negative 1, the value of the function f is also positive 1. So it goes to that number again. Now, when x is 2, sorry about that. When x is 2, then the value of the function when x is 2 is 4. Right? Because when we substitute 2 in this function, we get 2 squared equals 4. Okay? So in our drawing, we have when x is 2, then f is equal to 4. Okay? What about when x is equal to negative 2? What's the value of the function? The value of the function is again 4. Why? Because again, when x is equal to negative 2 in this function, negative 2 squared equals again 4. So when x is negative 2, I'll be here, then the value of the function is again positive 4. Take note that we can substitute any real number for x in this given function. And again, what's in the domain? Real numbers. What's in the codomain? Real numbers. So there are infinitely many numbers inside the domain and the codomain. Note that we can, again, substitute any number for x in this function. But take note, in the codomain, since this set contains all the real numbers, including the negative ones, such as, let's say, this contains negative 1. This number. Let's focus on negative 1 in the codomain. Focusing on negative 1 in the codomain. And then going back to the function f of x equals x squared. Or again, you may always write this as y equals x squared. Remember that we got these numbers 1 and 4, by substituting the values here in the domain in this function, right? So whenever x is 1, f becomes 1. Whenever x is equal to 2, f becomes equal to 4, and so on and so forth. So you think whenever x here in this equation, or in this function, whenever x here is any real number, do you think y, or f in this matter, will ever be equal to a negative number? Can y be a negative number, since x is always squared? I don't think so. Since x is always squared, y will always be a positive number. But what about in the codomain? Since the codomain always contains the real numbers, including the negative ones. So what happens to the negative numbers here, such as negative 1, negative 2, negative 1.5, negative 10, negative 100, and so on? Well, they are still included in the codomain, but they are not included in the range of the function anymore. I'll discuss the domain and range in the next video.